All right. So for number 17, ionic or molecular? Molecular. We got two non-metals. Okay. So I've got two nitrogens. What do I need to put in front of that? Right? That's the big thing. Okay. Dinitrogen trioxide. Good. Okay. Number 19. Ionic or molecular? Okay, and so what's that one going to be?
Nitrogen dioxide.
Nitrogen dioxide, right? I don't need a mono on the first one. Okay, now this is just to illustrate, okay, how we said you have to put prefixes in for molecular compounds because nitrogen and oxygen can go together a whole bunch of different ways. They're not concerned about balancing their electrons, they're sharing them. Okay, so they can share lots of different ways and have full outer shells and be completely happy. Okay, whereas with an ionic compound, like number 20, okay, there's only one way that hydrogen and sulfur can go together, and that's it. Okay, so what would we call this stuff? Hydrogen sulfide or sulfuric acid. Okay, if you go into anything related to like oil field stuff, drilling, okay, pipeline, things like that, you have to take a course about hydrogen sulfide. It is a gas often associated with pockets of petroleum, okay, and it can be released under pressure and be not only very dangerous because of the pressure release of the gas, but also because if you inhale it, it's an acid and it'll burn your lungs. Okay, so it's usually taken an H2S certification before you can work on an oil rig or pipeline and things like that. Okay. All right. Number 23. What are we looking at there? Ionic. It's ionic. Okay. And what's K stand for?
Potassium.
Okay. And nitride. Right. Do I need any Roman numerals in that one? No. Potassium only has one possible charge. Okay. Number 25. Magnesium fluoride, right, it's ionic. Okay. You guys weren't sure whether I wanted the name or whether I wanted ionic or molecular. That's all right. You were right on both. Okay. I think that was the last one I had on the board, right?
Yeah.
Let's try some names to formulas, because that's what we started yesterday. All right. I would like you guys to do the circled ones in red there, please. Okay, let's have a look at these ones. So I got number 5, phosphorus trichloride, ionic or molecular? Molecular. Okay, phosphorus and chlorine are both non-metals. So I'm going to have phosphorus, I'm going to have chlorine. Okay, how many phosphorus?
1.
Just 1, right. And how many chlorine?
3.
Okay, so PCl3. Okay, for number 8, I've got one with Roman numerals, cobalt-2 nitride, ionic or molecular?
Ionic.
Okay. So if it's ionic, then I go cobalt and I write the charge. Which charge do I use? Plus 2, because that's what the Roman numeral says to do. Okay, and it's with nitrogen, which is in group 15, so it's got a -3 charge. Okay, so what do I do now? Drop and swap, right? Okay, CO3, N2, good to go. All right, number 10, nickel 2 fluoride, ionic or molecular? Ionic. Okay, so nickel, and what charge is on nickel? 2 plus. Okay, it's with fluorine, which is in group 17, so it's a -1. So when we drop and swap, NiF2. Okay, manganese 4 selenamide. Okay, so what's the charge we're going to use on magnesium? 4, okay. Or sorry, I said magnesium, I meant manganese. Mn, and we got a +4, okay? And then we've got selenamide, Se, which is in group 16, so it is a -2. Okay, when I drop and swap, I'm going to get 2 and 4. Do I leave it that way? No. Okay, I reduce down to 1 and 2. Okay, so MnSe2 would be the correct version of that. Okay, is that an item that would be easy to put in a multiple choice question? Yeah, absolutely. Would I have both MN2SE4 and MNSE2 in there as possible answers?
Yes.
Oh yeah, I'm that mean. Okay, definitely I would do that. Okay, number 13, oxygen difluoride. Ionic or molecular? Molecular. Okay, how many oxygens?
1.
Okay, no prefix on that one. How many fluorines?
2.
Good. Okay, and then 16, disilicone octachloride. Ionic or molecular?
Molecular.
Okay, how many silicone?
2.
Okay, how many chlorines?
8.
Okay, should I reduce that one?
No. Yes.
Oh, good, it's chloride. Sorry, not oxygen, it's chlorine. I said chlorine and then I wrote oxygen. This is what happens when you get old. You do silly things. Okay, do I need to reduce that?
Yes.
No. Okay, molecular compounds never get reduced. Remember, they're not about balancing any charges. They're both negative. You can't balance a bunch of negatives. Okay, 2 wrongs don't make a right, but 3 do. Just kidding. That's a terrible idea to live by. Okay. Okay. So no, I don't reduce the molecular ones. They're sharing the electrons. There isn't like a lowest ratio that they can go together and be happy. This is how they're arranged. The prefixes tell me those numbers. Those are the numbers. Okay. I only reduce ionic compounds. Okay. All right. How are we feeling about the naming stuff? Pretty good? Okay, because that's what's kind of the bulk of the quiz tomorrow. There's a few questions on lesson 1, okay? About models of the atom, structure of the atom, a few important people, okay? I probably know the atomic theory, okay? The 4 points of the atomic theory, I'd say would be pretty fair game for that, okay? And then a bunch of naming and formula stuff, okay? So make sure that you're going over the notes from lesson 1, okay, in the notes package that's on Google Classroom. Go over that tonight to study partially for your quiz tomorrow, and do a little bit of naming practice tonight for your quiz tomorrow.
Is it multiple choice?
It is not. Yeah, it's going to be, there'll be a question, you got to write your answers in, okay? And I'm marking it, and we'll go over it on Monday. Okay? All right. Any other questions on those? Okay, then we're going to move into properties of compounds here, guys. Okay, so if you have your notes package there, it's lesson 4. Okay, if not, just follow along. Okay, so what we're going to go over in this lesson here, guys, are the properties and behaviors of both ionic and molecular compounds. Okay, we're going to talk about some of the properties, okay, that they may have, both mostly physical. We're not going to talk much about chemical properties today. That'll be later when we go over chemical reactions. Okay, today will be mostly about physical properties. And what we learn today is going to be useful when we do our lab on Tuesday. Okay? The lab on Tuesday is going to involve you getting 12 or 13 unknown compounds. Okay? They're just going to be at the front, and they're going to be in beakers about this size. Oh, we're going to use this one. It's got an A written on it already. Okay? There'll be a substance in there, substance A. Okay? And your job will be to run some tests on it, which we'll talk about today, okay? And determine its identity from a list. Okay? So you'll have a list of things that A through K are these materials. A is this one, B is this one, okay? And that's what you'll have to figure out based on just their physical properties. Now, right now you're probably thinking, well, that sounds quite daunting. Well, it actually isn't. Okay? I've only got a couple of compounds that are very similar, and they would only have one thing that would separate them. And there's a lot that are like, I can look at that and know what it is. Okay? So it's not as difficult as it might sound. Okay? There are a lot of physical properties, and thus a lot of different combinations of them that make everything a bit unique. Okay? All right. So let's start off with what are some physical properties.
Like how hard they are, like if it's super soft or if it's like hard?
Yeah, hardness. Okay, there's actually a scale, Mohs scale of hardness, M-O-H. Okay, Mohs scale of hardness. Like chalk is like 1 and diamond is like 10. Okay, and everything else is kind of in the middle there. Okay, it's why you can scratch glass with diamond and things like that's hardness. But yeah, definitely a physical property. Get you.
How about color? Like
Color, definitely, yeah. Color's an obvious one, right? If you look at something and it's blue or it's green, okay, that's a physical property.
What's the incident room temperature?
Right, so melting point, right? Boiling point, melting point, okay? Those are physical properties as well.
Viscosity?
Viscosity, if it's a liquid, how thick is it? Okay, water's not very viscous, but if you try and pour glycerin or honey, they're quite a bit thicker. Okay?
ductility.
Ductility, the ability to stretch it out into a wire if it's a solid, yeah, definitely.
I guess how acidic it is.
pH, yeah, basic or acidic, right? Where is it on the scale of pH from 1 to 14? Malleability, okay? If it's a solid, how easy is it to change its shape without breaking it? Okay? Like gold is especially malleable, okay? You can pound it and change its shape pretty easily without having to heat it up all that much.
Conductivity?
Conductivity, okay? Both, mostly talking electrical, but there's also heat conductivity as well, the ability to transmit heat. So definitely those would be physical properties. This is like one of the best lists ever.
Luster?
Luster, how shiny is it? Shiny or dull, okay? Most of the like metals that would be in this part of the periodic table are very dull, but of course as you move towards, you know, silver and gold and platinum, okay, they're much shinier.
Like their density, like how much mass?
Per cubic centimeter?
Yeah.
Yeah, density is definitely a physical property. Okay, if you got something like let's say you're comparing two rocks, two volcanic rocks, pumice, okay, is very light because it's mostly porous. It's full of a lot of air pockets, whereas like obsidian is the hard, just solidified lava that's just black and shiny. Okay, they would have different densities. All right, this is a good list, guys. Any others? I'm trying to think if we actually missed any. I don't think we did. That's good. All right, so we can use all of those properties, okay, to help identify something. We're not going to probably use all of those properties because, well, for one, we're not going to actually measure the melting and boiling point of all of the substances that we have. Some of them, their melting point is 600 degrees. We're not doing that, okay? But we can look at them and go, it's a solid at room temperature. Okay, that means it probably has a pretty high melting point. Okay, whereas if it's a liquid at room temperature, okay, its melting point must be, fairly low then, right? We're not going to have any gases. Okay, I mean, kind of look at our system here. All of the unknowns will be in beakers. It's not a very good way to contain a gas. I mean, sure, it's full of air, but I can't just like put carbon dioxide in there and go, here, sample this. So there won't be any gases. We won't have anything with a really low boiling point. Okay, all right. So, in terms of compounds, because that's what we're talking about now, not just elements, but compounds, okay, all matter has certain properties. Some are chemical, which we'll talk about later in the unit. Chemical properties always refer to how this thing behaves in the presence of this, okay? It's about two things going together and how they get along or don't get along, okay? Physical properties are the things I can observe about that thing on its own, okay? Oh, I know one we missed. Solubility. Super important when we're going to use in the lab, but we missed solubility, ability to dissolve in water. Okay, that's a physical property as well. Okay, so some of the physical properties, we listed a whole bunch: color, density, melting point, etc. Okay, they can be used to distinguish between different types of compounds, not just compound A and compound B, but this one's ionic because of this. This one's molecular because of this. Okay, there's quite a bit of differences in physical properties and behavior that way. Okay, so for ionic compounds typically exist as crystalline solids at room temperature. Ionic compounds have very high melting points, usually several hundred degrees. Okay? And anything that is a crystalline solid is generally referred to as a salt. Okay? That's why we don't use the word salt for sodium chloride. Salt is a general term referring to any crystalline ionic salt. I'm going to close those windows now. If I let any more cold air in, the heat will kick on automatically. Okay. Now, when we talked about ionic compounds, we talked about how that ionic bond is very weak. And what happens in an ionic bond is electrons are given away by metals and taken by nonmetals. So, when ionic compounds dissolve in water, the bond breaks. Those ions, those charged particles, separate and they float around in the solution. And because there are now charged particles floating around in the solution, the ionic compound's solution will conduct electricity. Okay? Distilled water, if you have absolutely pure distilled water, does not conduct electricity. Because water is a molecular compound. Okay? It shares the electrons, it doesn't trade them. Okay? So because of that, it doesn't conduct electricity. Okay? Nor do any molecular compounds when they dissolve in water. Okay? So I'll give you an example here, because I brought this stuff along today. Okay? This is some of the stuff we're going to use in the lab. Okay? This is a conductivity tester. Okay? An aqueous conductivity tester. So it's got two conductivity probes, okay, and a little button right here on the side. When you push it, there's an indicator light that indicates it's working, okay, and then when you put it in a solution, it will tell you the conductivity of that solution. So, for right now, I've just got, well, it's not perfectly distilled, but it's close, okay, water, and if I put the probe in it, you can see I've got a conductivity of 1. Okay, that basically means non-conductive. All right, so pure, basically distilled water, okay, basically no conductivity. Now, all of these beakers are filled with just plain water, okay? So what I'm going to do, let's move this, okay, is I'm going to put sodium chloride into one of them. Okay, so we'll put it in the one labeled J. All right, oh, sorry, just to make sure, because I don't want you to think like I'm one of those magicians and you're figuring out my tricks. Okay, same solution, still a 1. Okay. All right, so I put just a little bit of salt in there. Okay, here's another piece of incredibly technical equipment that you'll use, a stirring rod. Okay, now, most ionic compounds are going to be quite soluble in water. Okay, they'll dissolve fairly easily. I probably put too much salt in for the amount of water I had, but I want to get the point across. Okay, so it's pretty much gone. Okay, got most of it to dissolve there. So solubility is actually one of the things that is kind of an indicator of ionic compounds. Not all ionic compounds are soluble, like highly soluble, but most are. Right? If I do this thing now that I've got the salt dissolved in there, okay, like it's gone up to 7 or 8 now. All right, if I keep stirring because I still got some salt in there, oh yeah, there we go, just about popped up to 8. Okay, it's now highly conductive. Okay, so I went from having just plain water that's a molecular compound, okay, to having a solution of an ionic compound and suddenly it conducted electricity. All right, now just to be fair. If I do the same thing, but I use a molecular compound, right, that's the salt, that's the water. I gotta keep them straight. Okay, so this is just glucose, okay, which is a molecular compound, sugar basically. It's a highly controlled experiment. I put about the same amount in both. Okay, I didn't actually measure it, but that would have been better. Okay, why am I cleaning off the stirring rod and the probes in between?
So that you don't have any extra like salt water or something on that would screw up the.
Exactly. I don't want to transfer any of the ions over into this one that doesn't have any ions in it, otherwise it'll start conducting electricity. Okay? I actually couldn't find table sugar. I've never done this demo with glucose, but it should be the same thing. Okay? All right. So give that a stir. Now, this is a molecular compound that is soluble in water. Some are. Sugar dissolves in water pretty easily. Okay? But lots of molecular compounds are not. Think of like oil in water, right? Like oil is a molecular compound, doesn't dissolve in water. Okay, got that pretty well dissolved. Still a 1. Okay? There's no ions in there. Sure, it dissolved in water, but the compounds didn't break up into charged particles like the ionic compound did. Okay, so ionic compounds, they will conduct electricity in solution. Okay, you can't just like put the probes in the sample and go, nothing's gonna happen. Okay, it has to be in water first. All right, so distilled water will not conduct electricity. Okay, but if you're in an outdoor swimming pool and a thunderstorm comes along, do you have to get out?
Yeah.
Yes.
Yeah. If that pool was full of distilled water, would you? Not a bad idea to still get out, but okay, yeah, it wouldn't conduct electricity. Okay, but of course, swimming pools are full of all kinds of ionic compounds that they put in there to keep, well, gross stuff from growing in the pool. Okay, because yeah, it's a pool, and well, there's not like a peeing and a non-peeing section in the pool. Okay, it kind of just goes everywhere. Okay, so yeah, you got to be careful in there. But they do put a whole bunch of ionic compounds like shock and like chlorine and all that kind of stuff in there. Okay, and those compounds would make that solution conduct electricity very well, and you wouldn't want to get fried.
So what type of chlorine would they put in the pools? Like, would they just, like, what would they mix chlorine with to put it in the pool?
It's usually another ionic compound containing chlorine, like sodium hypochlorite or things like that. They don't actually bubble chlorine gas through the
Yeah.
pool water. Yeah. Okay. All right. So they conduct electricity when they're in solution. That's going to be important to help us identify compounds next week. Okay. It's going to be one of those important properties. Okay. When they are in solution, that is dissolved in water. Okay, they typically dissolve easily. Okay, on the last slide we said they're crystalline, or sorry, on this slide we said they're crystalline solids or salts at room temperature. Now, does that mean that if I see a clear crystalline solid, okay, I'm looking at it and go, oh, that's definitely salt, okay, or that's definitely an ionic compound? Am I going to be right?
No.
Sugar's a crystalline solid at room temperature, isn't it? Okay, I mean, you can, it's sometimes if you really know what you're looking for, you can tell sugar typically has larger crystals and they're slightly a different shape than sodium chloride does, okay? But, you know, you generally can't just go, that one's sugar, that one's salt, okay? And there's no taste tests, okay? I mean, one of the samples is hydrochloric acid, okay? That's bad for you, in case you didn't know that already. Okay, and another one is sodium hydroxide, which is the active ingredient in oven cleaner. Okay, also not good for you. Okay, so because you don't know what the unknowns are, you can't just go, I think that one is. Okay, because otherwise, yeah, you know, it'd be like drinking a spoonful of Drano. Okay, sure, it'll clean you out, but it'll leave you hollow inside. Okay, so you don't want to do that. No taste tests. Okay, what if I want to smell? There's another one we didn't talk about in physical properties, right? The odor of something. Some things have a distinct odor. You gotta waft it. Okay, so if I've got an unknown compound, okay, and I'm holding it here, I'm like, this is how I smell it. Okay, and guys, I make the solution super concentrated. Okay, so if they have an odor, you're definitely going to smell it. Okay, if you're doing this and you don't smell anything, it doesn't have an odor. Don't do this. Okay, some of these are quite powdered, and inhaling sharply over top could result in you snorting them. Okay, and that would be bad. Okay, also, a solution of hydrochloric acid does go into vapor fairly quickly. Okay, were you to snort it, you would probably be on your back bleeding from the nose. Okay, so I don't want that for you. Okay, lab safety, okay, we want to just waft the things, and if we detect an odor that is obvious, we record it and write it down.
But isn't that not like the best idea because of what you said, like,
If it goes into a vapor,
yeah, cause like,
it's not gonna be enough to hurt you, and at the end of the lab, everybody has to wash their hands.
okay,
Okay, it's not nitric acid, okay, and it's not super concentrated. Like nitric acid, you have to wear gloves if you're gonna hold your hands over the open bottle of it, okay, or you would have chemical burns in minutes, okay? The hydrochloric doesn't do that as much, yeah? And it's not gonna be that concentrated, okay? Like you spill it and it, you know, it's like an alien, and the acid drills a hole in the countertop, okay? All right. Everybody with me so far? Okay, so crystalline solids, okay, would all the ionic compounds crystals look different?
Yeah.
Yes, okay. In fact, if you take university chemistry, okay, one of the things you do when you're looking at different ionic compounds is they actually have kind of a special microscope for looking at the crystal shape of certain ionic compounds, and you get like hexagonal, tetrahedral, okay, all these different crystal shapes, okay, for each ionic compound. We don't have that equipment, and it isn't going to matter for us, but it's a physical property as well, okay? And some ionic compounds have distinct colors, okay? So that's our next slide here, I believe, okay? So the big ones will be, okay, copper-containing compounds will be blue. Okay, nickel-containing compounds will be green. Okay, and cobalt-containing compounds are pink to red. Okay, so if you got something and it's kind of a bright blue color and it's a crystalline solid, it's probably an ionic compound containing copper. Okay, if you got something that's green and it's a crystalline solid, then it's probably a nickel-containing compound. If it's a little red or orange or pink, okay, then it's probably a cobalt-containing compound. Okay. Now, are there exceptions to those rules?
Yeah.
Yes, not for these. All copper-containing compounds are blue. All nickel-containing compounds that are green. Okay, but there are other elements that can produce those colors as well. Okay, some iron-containing compounds are orange. Some iron-containing compounds are green. Okay, there's no hard rule for the color of iron. Okay, there are hard rules for cobalt, nickel, and copper. Okay. All right. So can that help you with an individual identity?
Yes.
Yeah. Okay.
cause like, as you said, others, like, sometimes it has different colors, not based on those,
Right.
but it can help you narrow it down.
Yeah, it can give you more evidence to say, I believe that A is copper 2 sulfate. Okay? So if at the end of my lab, I'm looking at this thing, I know it's a blue crystalline solid, okay? It dissolves easily in water, its solution conducts electricity, okay? It's fairly neutral in terms of pH, okay? It doesn't have any discernible odor, okay? Things like that. Then I could probably pretty safely say that stuff would be, if one of the identities on my list was copper 2 sulfate, I'd say that's probably what this is. Okay, I'm not going to be a jerk and put in two things that are green, one iron and one nickel. That's hardly the point of the exercise. Okay? All right, so everybody got those ones down? Because those would be helpful. Okay. Now, molecular compounds, okay? Yeah, can there be crystalline, solid molecular compounds? Absolutely there can, but they're not all that way. Okay? Molecular compounds typically are not crystalline, typically, okay? And they typically have lower melting and lower boiling points. Okay, molecular compounds are not usually as soluble, okay? There are exceptions, not usually as soluble. And as we saw a few minutes ago, their solutions will be non-conductive or have a very low conductivity. I would say if you get a conductivity reading of 4 or less out of 10, okay, you're probably dealing with a molecular compound. Okay. So if I'm looking at my unknowns, and I got a beaker that's got a liquid in it, what can I eliminate as possible identities from the list?
It's probably not an ionic compound because ionic compounds are crystalline salts.
Yeah, exactly. If I've got an unknown compound that's a liquid, it isn't any of the unknown compounds on the list. Right away, I'm probably going to eliminate, I think it's about 2/3, okay, of the compounds on the list, okay? Ionic compounds are crystalline solids at room temperature. So if I got a liquid, I know it isn't any of those. Okay. All right, making sense on kind of the thinking process that we're going to want to go through for that lab? All right, now, molecular compounds that are soluble in water usually produce colorless solutions. Okay, you're not going to get like, you know, if you have something that's got copper in it, you put it in water, the solution's going to turn blue. Same with cobalt, it's going to turn red. Okay, same with nickel, it's going to turn green. Okay, molecular compounds typically make clear solutions. Is it possible for a liquid to be soluble in another liquid?
Yeah.
Absolutely. Okay, alcohol is soluble in water. Okay, if you were to pour like, you know, rubbing alcohol into just tap water, okay, it would dissolve just fine. Okay, it wouldn't sit on top or settle to the bottom. Okay, so yes, it is possible for one liquid to be soluble in another.
What if you have like nickel and like copper, both in like a mixture? Like, what color would it be?
Well, nickel and copper won't go together. Metals won't bond with each other.
Do they feel like sit on top of each other or not?
Oh, if you mean if I put them in the same
Yeah,
solution?
the
Oh,
same solution.
okay, so ionic compounds don't dissolve in other ionic compounds. If I mixed them both in water together, it would come out somewhere in the middle. Yeah, just like mixing colors together, right? There wouldn't, unless there was a chemical reaction between the two. That would be the concern, right? If I put two ionic compounds in a solution together, they might react. Then I might get something else entirely, right? When we do our reactions lab, we'll have one reaction where we mix two clear solutions together, both containing an ionic compound, and we get a precipitate out of it, right? It turns bright yellow, okay? It just settles right to the bottom. So that's probably more likely what would happen. Okay. Now, acids. Okay, we got to talk about acids and bases here. Okay, there are strong acids and weak acids, and there are strong bases and weak bases. Okay, strong acids are ionic compounds where hydrogen acts as the metal. Okay, so acids are compounds that have hydrogen plus ions in them. Okay, that means an ionic compound with hydrogen acting as a metal. Okay, the strength of an acid is based on two things. The first thing is how quickly the dissociation happens. Okay, now what I mean by dissociation is how quickly does the ionic compound come apart? Okay, that's dissociation. Okay, how quickly does it break into its two charged particles? Acids typically dissociate very quickly. Okay, some dissociate quicker than others. Right? It depends what hydrogen is bonded to. Okay. The other thing that determines how strong an acid is how many hydrogen ions it can donate to the solution. Okay, so when it dissociates, does it give one hydrogen ion, okay, or does it give more than one hydrogen ion? So let me pose this to you. Which of these acids would be stronger?
Hydrogen sulfide.
Hydrogen sulfide. Okay, sulfuric acid would be stronger because when it dissociates, it puts two hydrogen ions in the solution, where hydrochloric acid only puts one in solution. Okay, making sense? Remember I mentioned nitric acid a little while ago, how the vapors can give you chemical burns, okay? Okay, H3N. Every time that dissociates, 3 hydrogen ions are going into the solution. Okay, that's actually what pH means. Okay, the P is lowercase, it's power of hydrogen. It's a logarithmic kind of thing, but it's pH basically means how much hydrogen ion is in this solution. The more, the stronger it is. Okay, now acids are on what end of the pH scale? Low, right? Acids are below 7. Okay, strong acids are typically like 2 or lower, but it's based on their concentration. I can have a solution of hydrochloric acid that only has a pH of 4, okay, provided I dilute it enough. Okay, it's again how many hydrogen ions are in that solution. Okay, if I take just the pure stuff, it's going to be really strong, but if I start diluting it, the number of hydrogen ions per liter goes down. Okay, everyone okay with that idea? Okay. What do we use? What's a common place where you might find hydrochloric acid? Yes. Your stomach. That's stomach acid. Your body actually creates it, secretes it into the stomach. It helps to break down proteins in your stomach. And that's why stomach acid is there. It's hydrochloric acid. It's weak. It's like a pH of 2. Okay, well, weaker. Okay. But it's strong enough to digest your food. Why doesn't it digest your stomach?
There's like a mucus, I think, like kind of like a layer of mucus.
Exactly, yeah. Your stomach lining, the cells in your stomach lining secrete a layer of mucus constantly, okay, on the inside of your stomach that protects it from the hydrochloric acid. The hydrochloric acid eats it away and your body just makes more of it, okay? So if you've ever been like, this is gonna be awful, some of you might not like this, but if you've ever been like really sick and you vomited a lot, okay, you're bringing up a lot of that stomach lining at the end, okay? It's kind of like, you know, mucusy, yeah. You're basically puking up your stomach lining at that point, okay? You ever had heartburn? Okay, heartburn happens when a little more stomach acid is present than should be, and it actually gets past the little muscle that's at the top of the stomach and gets into the esophagus. Okay, the esophagus doesn't have a mucus lining. Okay, so when you get heartburn, it isn't your heart that's burning, it's your esophagus. Okay, your stomach acid is literally burning your esophagus a little bit.
Yes.
Okay,
They lied to us.
who did? Oh, the people that made up the expression?
Yeah.
Yeah, well, I mean, it feels like your heart, right? Like it's right here. When you get heartburn, it's here. It's sometimes even a little bit higher than that if you've got acid reflux, okay? That's the acid going up into the esophagus, okay? If you have too much stomach acid for a long period of time, what might happen?
It could eat away at your esophagus.
Right, anyone know what that's called? It starts with a U. You guys heard of an ulcer? Okay? An ulcer is when your stomach acid burns some part of your digestive tract that it's not supposed to. Okay? So you can get a gastric ulcer, that's actually in the stomach. You can get an esophageal ulcer, that would be in the esophagus, and you can get a duodenal ulcer, which is the first part of the small intestine after the stomach. Okay? So it's pretty acidic enough that it can, give you a chemical burn basically inside your body. Okay? You can just rock yourself to sleep tonight with that thought. Okay, now acids will have obviously a low pH. They're going to turn our pH indicators to acidic colors. The pH indicator that we're going to be using, okay, are these little Hydrion papers. Okay, so when you take these out, it's just a piece of orange paper. Okay, you just take one little piece of it off. Okay, one little piece of it can test 2 solutions. Okay, just rip it in half or test both ends. And then once you dip it in the solution, you right away compare the color to the color chart. Okay, and from there you can get an approximate pH, and that's really all we need, right? When we do this lab, pretty much everything is going to be somewhere between 5 and 8. Okay, and then you'll have like 2 that are, one that's like 14 and one that's 1. The scale actually only goes up to 12. But the solution I made is in the past made this thing turn black. Okay, so that's like 14 for sure.
Is it? Well, is it? Don't humans have like a bit of acid in their saliva?
Your saliva's pH is maybe slightly acidic. It might be like a 6 or a 5 maybe. That's not a strong acid, but it's not neutral either.
So do you just dip that paper in, or do
Yep.
you like dip it in for a few seconds?
No, dip it, check it right away. Yeah, if you leave it in there, it's not as valid, right? And if you dip it and then set it down and come back to it 2 minutes later, do it again, okay? Dip it, check it right away. Okay. All right, now, one that we're not going to check. Okay, acids taste sour or tart. Okay, but there are no taste tests. Okay, it will be the last thing you ever taste. Okay, if you taste test the acid and the base in here. Okay, but they do typically taste sour or tart. Okay, I mean you've had like a grapefruit or a lemon, right? They're acidic. They have a lot of citric acid in them. Okay, so they are tart. Okay, or sour. So they typically taste that way, and they often have a vinegar-like smell. Okay, so if you've ever smelt vinegar, vinegar is actually a weak ionic acid called acetic acid. Okay, but most acids have that kind of curl your nose hairs kind of a smell to them. Okay, it's a bit like vinegar. Okay, would be my description. Okay, you know, if it smells like burning, you've snorted it, not wafted it. Okay, but yeah, they typically have that kind of property to them in terms of odor. Okay. All right, questions on the acids. Okay, so acids are because of H+. Okay, bases are because of OH. Okay, so bases have OH or hydroxide ions in them. Okay, so the compound I just wrote there on the board, sodium hydroxide, NaOH. Okay, that is a very strong base, right? Because it is an ionic compound and the non-metal is hydroxide. Okay, so strong bases do the same thing as strong acids. They dissociate very quickly, okay? And the more OH that can be put into the solution, the higher the pH is going to be. Right? Making sense there? All right, so then, what would this stuff be?
A very happy face or a surprised face.
Yes. What else?
Neutral.
Neutral. Because what is that? That's water. Right? H2O. But if I write it HOH, still the same thing, but I've got the thing that's most acidic and the thing that's most basic together. Okay? Water's neutral. It's got hydrogen and hydroxide. Plus it's molecular, it doesn't actually dissociate. But okay, we sometimes actually in a reaction write water like this and make it behave like an ionic compound. Okay? Because water is weird. Okay, we're gonna like half a lesson here later that's all about water and why it's weird. Okay, but if there's a rule in chemistry, water's almost always the exception to it. Okay, it just does a lot of weird things. Okay, so bases have OH ions in them. So anything that is an ionic compound that ends in OH is probably going to be basic. Okay, now would this stuff be basic?
No.
No. Okay, that's a molecular compound.
That's acidic.
Anybody know what that is? During COVID, you used a whole bunch of it. Yeah, it's alcohol. It's ethyl alcohol. It's actually the stuff that's in booze. Okay, but it's also what's in hand sanitizer. Don't drink hand sanitizer. Okay? There's other things in hand sanitizer that are definitely not good for you. Okay, but when there was a real shortage of it, we actually made our own using the materials in the lab. okay? So it's ethyl alcohol, but it's not basic, okay? Because it's not ionic. If I put that in water, it's just gonna dissolve, okay? It's not gonna dissociate. It's not gonna lose this hydroxide group, okay? In fact, it's not really even a hydroxide group, it just doesn't behave that way, okay? So that's not gonna be a strong base, but that is. What about this?
Yeah.
Yeah,
Yeah.
that's lye, okay?
Seems-
It's what's in soap. Okay, and if you've ever watched any like murder shows on like the murder channels on TV, okay, this is the stuff that they use to dissolve bodies. Okay, like if they, any of the, the serial killers that want to dispose of the bodies, they'll put lye on them. It destroys the DNA, it dissolves just about everything. Okay. I'm not trying to help you plan a murder. Okay, I'm telling you this is what people have done. Okay, but that's lye. Lye is also if you like if you have a porta pot, an outhouse, not a porta potty. If you have an outhouse, okay, lots of times they'll throw lye in it because it would keep the smell down. It kills all the bacteria that would be in the fecal matter, okay, and keeps the smell down, right? So we use it for things like that as well. Okay.
So, are the bases and acids only for like ionic compounds or molecular?
Only the strong ones are ionic. You could have like weaker ones, like citric acid is a weak acid. It's not an ionic compound. Okay, it's a molecular compound.
Yeah, but ionic compounds are
Gonna,
strong.
yes, are gonna be your strong ones because they dissociate.
Alright.
Okay. In fact, you have to be careful when you're making the solutions of these things because they dissociate. They come apart so quickly that they actually release a lot of thermal energy. Okay. So when I'm making a solution of acid for this lab, okay, I have a fair amount of water and I slowly add the acid to it because water can absorb that energy pretty quickly and pretty well. Okay. If I go the other way, if I add water to the acid, it'll get so hot so quickly that it'll often break the container. Okay, it just rapidly gets really, really hot. Okay, so when we're making the solutions, you're always adding the acid or base to water. Okay, not the other way around. All right, so that's what that dissociation causes. All right, typically bases taste bitter. Okay, if you ever swore as a kid and got your mouth washed out with soap. Okay, if you ever seen like the Christmas Story, right, that happens in there. Okay, that was something parents used to do back when I was a kid. Okay, I got my mouth washed out with soap. It tastes bitter. Okay, if you ever accidentally got in your mouth in the shower, it tastes bitter because it's got lye in it. Okay, it's got a base in it. It's basic. Okay, but we're of course not going to taste test anything. But the next time you taste something and it's bitter, it probably is a base. Like baking soda, for example. If you ever tasted baking soda, it's bitter. Okay. All right, and then obviously basic solutions have a pH higher than 7, and they're typically going to turn pH paper type indicators to bluish, darker colors. Okay. All right, everybody good with that? Okay. So all of this stuff that we covered today is going to be helpful for identifying our unknown compounds. Okay, in this way. You're going to collect a lot of information on their physical properties, but also you're going to know that these are the possible identities for A through K. All right, so when you're looking at the identities, you can go, all right, copper sulfate, okay, well that's going to be blue and it's ionic, so I just have to look for something in my unknowns. Oh, when I tested sample C, it was blue and it was ionic and blah, blah, blah. Okay, you can kind of predict, okay, this is, NaOH. That's an ionic compound, so it's probably going to be very basic. What do I have over here that's ionic and basic? Okay, and then kind of do that kind of matching. Okay, does that make sense? All right, so that will cover all of the properties of compound stuff that we need to know. Okay, I'm going to talk a bit about some of the equipment that you're going to use, okay, on Tuesday in the lab. All right, so I already showed you the conductivity tester. Okay, it's just a 9-volt battery on top of this little indicator thing. Okay, you push the button, and should you rinse that off every time?
Yes.
Should you rinse it with tap water or distilled water?
Distilled.
Yeah, okay.
Thermometer.
Thermometer. Okay, so obviously you probably use one of these at some point. Okay, what's the little rubber thing for? Yeah, if you got it in a beaker, you can kind of put it down there so that it won't tip over. Okay, but mostly it's to insulate against the heat of your fingers. Right? If I'm grabbing, so I see people do this. They got it in their fist and they got it in. You're not measuring the temperature of the solution. You're measuring the temperature of your hand. Okay? So if your thermometer has one of these rubber things on it, that's what you want to hold it by. If you don't, hold it as close to the top as possible, so as few of your fingers are on it as humanly possible.
May I just go to the
You
bathroom?
may. All right, and then obviously, you read the temperature off of here. Okay? It's a very high-tech device. All right. Anybody used one of those before?
Is that a miniature egg tray?
It's not an egg tray, but it kind of looks like maybe you colored eggs at Easter, kind of like that. Okay, but no, this is called a depression plate. Not because it's sad. Okay, it's not like that at all. Okay, it just has holes or depressions in it. Okay, that's what you're going to put your unknowns in. Okay, so we're going to have 11 or 12, so you're going to have to do this twice. Okay, so put your first 6 in there, and then you can, check them out and go, okay, well that one's crystalline and it's green, and I'm going to write all that down, and it doesn't smell, or you probably want to smell the actual sample up at the front, because if you do this, you're smelling all of them at once. Okay, so you probably want to smell the original one. Things like that, right? You can do all of those kinds of observations in here. You can test the solubility in here, so you'll add a little bit of distilled water, give it a stir, okay? Take the temperature while it's dissolving to see if the temperature changes, okay? Because we were just saying, when you dissolve an acid in water, or a base in water, what will happen? What will happen to the temperature?
It'll increase.
It'll increase. Okay, so things to watch for, right, when you're checking whether it dissolves in water. It might dissolve really well and get hot. Okay, those are all valid things to record. Okay, then we would check the conductivity of that solution that you just made with the conductivity tester, and then at the very end, we would put a piece of pH paper in there and test the pH. Okay, I mean, that's basically going to be your lab on Tuesday, just kind of checking those kinds of things. Okay.
Wait, so if you have like some liquid and you're gonna try and find the solubility of it, would you like get that out of there to put some water in before?
No, you're going to add water to everything. So you're going to have your unknowns, even if they're a liquid, in here. And then you're going to have the wash bottle, squeeze bottle, and you're going to add the water to it. If it doesn't separate as a liquid, then it's soluble.
Yeah, but didn't you say that like one liquid would get like really, really hot if you added like water to it?
I said some acids and some bases, but they'll be crystalline solids.
Alright.
Okay, it's a good question, safety question.
Will we be in like groups or by?
Yes, I'm actually making up the groups today. Okay. Other questions before I go to safety stuff? Okay. So that you have lots of notice for Tuesday, okay? On Tuesday, you must have footwear that covers your feet, okay? No open-toed shoes, sandals, flip-flops, or anything like that. Okay, you actually have to have shoes, okay, that cover your feet. Even if you're wearing socks inside your sandals, because apparently that's coming back as a look. Okay, the last time that was fashionable, I was your age. Okay, so yeah, if you're wearing sandals and socks, you still need to have shoes for Tuesday. Okay, because if we spill something on the lab station and it runs off, and all you've got on is a sock, okay, or God forbid a bare foot, it's getting on your skin. Okay, so we need to have a shoe. If it gets on the shoe, you can kick the shoe off pretty quick. Okay, so you have to have actual shoes on for the lab.
Okay, so I have a hole in like the heel of my casual shoes. Why
That's
is
fine.
everyone looking?
You're good.
But okay.
Yeah. As long as you got something that's covering basically the top of your foot. Okay? I'm not worried about the heel. If you're standing in something acidic, you're in trouble. Okay? Yeah, you got your Achilles going on there, right? Yeah. So yeah, for safety, shoes first, okay? You have to have proper footwear for the lab. Okay? If you have long hair, put a hair tie in your science binder. Okay? Because when we do the lab, your hair has to be tied back. all right? I don't know how many times this has happened, but somebody doesn't have their hair tied back, they lean forward, hair gets in something, okay, and the whole lab smells like burnt hair, okay? And by the way, then your hair is also burnt, but you know, the rest of us are suffering the smell of burnt hair, okay? So make sure your hair is tied back if you have long hair, okay? Hoodies, anything with like drawstrings that can hang down, they gotta be tucked away, okay? We just don't want anything that's gonna get into anything else. So anything that's really loose you need to put something on that'll be tighter, okay? We have lab aprons, so you can put the lab apron on, okay, to protect your clothes as well. And then probably the most important one is safety goggles, okay? Every lab station has safety goggles in it, and you will go into the lab and put them on, okay? And they will stay on until I tell you it is safe to take them off, okay? Just because you're done doesn't mean it's safe to take them off. There are people around you that are still working, okay? So safety goggles have to be on because I do not want to have to shove anybody's face into the eye wash again. Okay, it isn't fun for anyone. Both people usually end up bloodied after the whole thing, so we don't want to do that. Okay, it's not fun. So goggles on at all times, hair tied back, okay, proper footwear, those are the big things. Okay, in terms of behavior, move purposefully. No horsing around, okay? Anything that I deem to be obviously unsafe will result in your removal from the lab, okay? And there's no warnings on that, okay? If you're fooling around, you're out, okay? Safety is paramount, especially with 32 of us in a lab designed for probably more like 25 people, okay? So we have to be really mindful about our movements and behaviors when we're in there. When you leave the lab, wash your hands, okay? That's pretty much it, lab safety wise. I wouldn't wear my favorite clothes to the lab, okay? Maybe you wear something, you know, a little older, you care a little less about, okay? Like I'm definitely not wearing my Oilers jersey into the lab, okay? It's decorated with wing sauce, it doesn't need, okay, other things on it. So don't wear your favorite thing because it's generally not good. You're lucking out. Picture day is late this year. I almost always end up with this lab on picture day and everyone gets to go in with the goggle marks, okay, for their picture. If you're wearing glasses, prescription glasses, you still have to wear goggles. I'll give you the bigger ones that fit over top, or that might be a good day to wear your contacts if you also have contacts. Okay, I typically wear contacts on lab day just because it's easier. Okay. Any other questions about lab? Okay, perfect. What was the other thing I was going to tell you? The degree to which I forget something is directly proportional to its importance. Anyway, okay, so for tomorrow's quiz, okay, how many people have done at least one of the 2 practice quizzes? Okay, good. Definitely do that. Do some practice from those worksheets. Okay, that's probably what we'll finish off class with here, is just a few more questions from the worksheets. And then Monday we have the computers. Okay, so we'll do lab reports and start the pre-lab. And then Tuesday will be the lab. Okay, and then we'll be moving on to solubility, polar nature, water, and reactions. Probably get into reactions next week. Okay? All right. Then, let's have you guys do you can. Okay, try those 5 circled ones, please.